In this part of the lecture, I will talk on the sound synthesis. This is an important part of the product sound design process. Therefore, we will now discuss about different aspects and techniques. But before I start with different techniques, I would like to give a very short information on audio signals. I know that in the lecture, Fundamentals of Signals and Systems, you get already some information, but I would like to repeat it very shortly because they are very important for the sound synthesis. And I would like to start with tone. It is, of course, very important signal for us. It is steady periodic sound. At the end, sinusoidal signal, sinusoidal waveform, which we see in this slide. I have prepared different frequencies, for example, 450 Hertz, 880 Hertz, second harmonic, third harmonic, 1320 Hertz, and I make some of them. And at the right side of the slide, you see also in the frequency axis some lines. They show the frequency of these signals, which we see in time domain. I would like to play first 440 Hertz. And if I play 880 Hertz, you notice that these signals sound very artificial. Also, if I play 1320 Hertz, in most cases in our daily life, always we have complex signals. For example, sum of them. If I sum of all them and play it, it sounds much more musical. And therefore, tone is for us quite important for sound synthesis. Also, amplitude modulation is an important aspect, and also amplitude modulated sinus tone. And in that case, we are talking about, we have a carrier signal, a sinusoidal tone, and we modulate the amplitude of the carrier wave. The frequency will be constant on the time, over the time. And depending, of course, in the second picture, we see that amplitude modulated signal over the time axis, and the depth of the modulation is very important for the feeling. We use for it modulation degree. And I would like to play now, first of all, a sinusoidal signal, for example, a tone 440 Hertz. And if I modulate it with 4 Hertz, we notice that it sounds very different, but we can follow the fluctuation. And if I play 40 Hertz, we notice that it sounds very different, and in that case, we cannot follow this fluctuation. And the interesting point is that if we look the Fourier analysis of this amplitude modulated signal, we see in the frequency axis 3 components, 3 red lines. One of them at the carrier frequency, 440 Hertz, and one of them is 440 Hertz minus 4 Hertz, 436, and the other one, carrier frequency plus modulation frequency, it is 444. It means that if we add 3 sinusoidal signals, at the end we can also get a modulation. In normal case, amplitude modulation can be realized if we multiply 2 sinusoidal signals. It is also possible to modulate the frequency. In that case, we have again a carrier signal and we modulate the frequency of it. The amplitude will be constant, and depending on the modulation index, we have different number of sidebands. In our example, I used a carrier frequency of 300 Hertz. I modulated it with 50 Hertz, which is very common modulation frequency in electrical systems, for example. And I also used a modulation index of 4. I would like to play, first of all, 300 Hertz. Sinusoidal signal. And if I modulate it with 50 Hertz, you notice that it sounds like old refrigerator, because most of the household appliances, of course, use 50 Hertz as network frequency. At the same time, of course, we don't have only sinusoidal signals, we have also noises. In that case, we are talking on stochastic signals which have broadband spectrum. In that case, I will show the white noise and pink noise. We have also brown noise. But in the white noise case, in this case, we have random signal with a constant power. Spectral density in the frequency range of 20 Hertz to the 20 kilohertz. And I would like to play it. And in the pink noise case, in this case, as you can see in this slide, the red line, at higher frequencies, we have lower power spectral density. Actually, this decrease means 3 decibel per octave. And if I play the pink noise, and now white noise, you notice that white noise sounds much more sharper in regard to pink noise, because at higher frequencies, of course, we perceive much more sensitive. Therefore, white noise sounds sharper. Now, I would like to discuss different techniques for sound synthesis after the signals, test signals. And we have different possibilities for the sound design. For example, wavetable, additive synthesis, subtractive synthesis, frequency modulation synthesis, model synthesis, waveguide, or others. And of course, because of the limited time, in this lecture, I will concentrate on 3 of them: additive, subtractive, and model synthesis. Before I discuss the additive synthesis, it is also very important the time or temporal envelope for the sound synthesis. We apply, in most cases, such kind of temporal envelopes which contain 4 different, actually, parts. One of them is the attack, the other one is decay, third one is the sustain, and fourth one is the relays. Particularly, attack, delay, and relays are very important to give a natural, to produce a natural sound design. And in the attack case, we are talking about how quickly the sound reaches the full volume. In the decay part, we are talking about the time the sound drops to the sustain volume after the initial peak. In the sustain case, we are talking about the constant volume, and at the end, we have a fade out, the relays part. And we apply this kind of envelopes to different sound synthesis products. And I would like to start with additive synthesis. In this case, the idea comes from the Fourier. Actually, Fourier said that we can separate the complex sounds to the individual sinusoidal components. Of course, it is also correct vice versa. It means that I can make a summation of individual tones, and at the end, I can generate a complex signal. Therefore, as we can see in this slide, in this basic idea, we use different sinusoidal signals and add to them. Of course, the amplitude of these sinusoidal signals are always different depending on the aim. For example, A1, A2, A3. And of course, the frequencies are also different. This kind of sound synthesis is quite nice. Of course, for steady sounds, for example, for electrical motor, if we make a sound synthesis for electrical motor, in this slide we see the acceleration aspects of the electric motor. Sound generation aspects are very similar. We have very clear, distinct frequency components, sinusoidal tones. And of course, we can use additive synthesis to generate or design such kind of sound very well. There are also other, of course, product sounds, for example, refrigerator noise. In that case, we have some sinusoidal components, which we see in this picture, but at the same time also a background noise floor, and therefore also in such cases we add a noise floor to our additive synthesis to generate such kind of signals. As we can see at the first analysis, for example, in refrigerator case, we have also amplitude modulated sinusoidal components. In that case, of course, we should take into account. That means that we can make further analysis for additive synthesis. Also, in some cases, of course, we have some transient sounds, for example, guitar or musical instruments or different other products. In such cases, of course, addition of the decay time is quite important to give a feeling that for the sound drop. In the next part, I would like to discuss subtractive synthesis. In this time, we begin with broadband noise or pulse, and our aim is to remove other components which are not interesting for us. For example, we filter the partial components of the audio signals, we remove them from this broadband noise or pulse. Of course, this kind of synthesis is very useful if we should generate or design noise-like signals. For example, such kind of rubbing or friction-based noises. And therefore, we use subtractive synthesis, much more noisy signals. There are also other possibilities for the synthesis. One of them is the model synthesis. I will shortly discuss on it. In this case, we try to model the model behavior, vibration behavior of objects. And of course, in that case, we have complex dynamic behavior, and we can decompose this complex behavior into contributions of a set of modes. Therefore, in this picture, first of all, we see a string and mass and springs we can use to simulate the model behavior of it. As I already said that, for us, quite important issue also modes. Therefore, we use different modes and take into account for the synthesis. First of all, we see the first mode plugged in the center, and then we see odd modes and also even modes in this slide. Therefore, we use some computational models to simulate the acoustical waves. A lossless digital waveguide realizes the discrete form of D'Alembert's solution of the one-dimensional wave equation as the superposition of the ongoing and backgoing waves, left and right-going waves. And for that aim, we use actually delay lines as digital filters. It means that digital waveguide principle comprise digital delay lines to represent the geometry of the waveguide, which are closed by recursion. And at the end, we can generate different sounds using digital waveguide. In most cases, of course, one-dimensional cases, we use membrane or similar kind of aspects. In some cases, we should take into account three-dimensional aspects.